In this video, we are going to extend ideas from the last video where we were looking at the ways that we can evaluate limits from a graphing perspective. But now we'll look at the algebraic laws that allow us to evaluate a limit without having to put a graph together. Here are a list of some of the basic rules that we have when evaluating limits. We're going to assume that we already know what the limit of two particular functions are. We're going to use the functions f and g in this case. And so we're going to start by saying, okay, the limit of f of x exists and also g of x as we approach this same point A. Moving from the left and the right together, both of them are approaching the same value. Not f and g, but if I'm just looking at f, the left-hand limit and the right-hand limit are the same. If I'm just looking at g, the left-hand and the right-hand limit are the same. So these both exist. I have some basic algebraic ideas to combine these functions together. If I wanted to consider the limit as x approaches a of the sum of these functions, I can separate them and look at the limits separately. Similarly, if I want to find the difference of these two functions, I can separate them and subtract the two limits. The third example is showing us that if we have a constant that's being multiplied in front of the function, we can bring that constant out into the front, take whatever the limiting value is, and then just multiply by that constant. The third is the product law for multiplying two functions together and then separating them into a multiplication. And then the third is the quotient, where we are dividing the two functions. Of course, we need to keep in mind that whatever the function is in the denominator, that limit cannot be equal to 0 because we can't have 0 in the denominator of any fraction. Let's use these ideas to evaluate a function. Here's a function that's two functions that are defined differently. The pink is the function f, and the blue is the function g. They're two separate functions. For the first example, we're going to evaluate what is the limit if we were to take the function f and add it to 5 times the function g. And I'm going to consider what's happening as I take those two functions, adding them together, and what's happening at -2 as I approach x equals -2. The first thing I'm going to do is think about what's happening with the two individual functions, f and g, separately as they approach -2. So looking at the graph for f, if I go to where x is equal to -2, which is over here, for the function f, at -2, it's defined up here, right? But if I think about the limits, left hand and right hand, they're approaching 1. So even though the function is defined in a different place, the limit as we're approaching from the left and the right is the value 1. Let's look at the function g next. When we look at g, that's the blue function, also at x equals -2. Right here, the function value is -1. We're approaching from both the left and the right, and they're closing in on the same value. So now putting these two ideas together, I want to know what the limit is if I add f and 5 times g. That sum rule that we saw on the last slide says that we can separate this into two separate limits. I'm separating it into the limit of f of x and the limit of 5 times g of x. So the first thing I do is separate them. The second thing I'm going to do is take that 5, which is a constant, and bring it out into the front. Now, what I just figured out by looking at the graphs above is that the limit for f is going to be 1, and the limit for g is going to be -1. That's what I looked at up here. And so then just putting those numbers together, I get that my final output, my answer in this case, is going to be -4. By looking at the picture of the graph there, there's no way that I would have been able to determine that, because this is not a function that I could easily add or subtract to get a different picture of. So I'm looking at this algebraically instead. In this example, same function, but we're going to look at multiplying these two together. And this time we're looking at what happens as x approaches 1. So here's where we're looking at the two functions. For f, as x approaches 1, the function is closing in on the output value of 2, right? So that's here. When we look at g, we're here at 1. If I look at the left-hand side, the function is approaching, it looks like -2, but from the right-hand side, it's approaching -1. Because it's not closing in on the same value, the limit does not exist. The right and the left-hand limits are different. So in this case, we can't determine what the overall limit is going to be because one of them is undefined. So in this case, the limit does not exist. What I mean is this limit cannot exist because g, that one doesn't exist. So we can't combine those two together. Here is an example of a quotient. And we're looking at what's happening as the graph approaches x equals 2, which is over here. For the function f, it looks like the graph is approaching about 1.4. And for the function g, it looks like the graph is approaching 0. Well, unfortunately, we're not able to evaluate the limit because since g is the function in the denominator, and we can't have this equal to 0, in this case, we also would say that the limit does not exist. We do have some additional limit laws to think about. If we take the product law and we repeat it over time, like if we multiplied the same number together and over and over and over again, we would get this power rule, right? If we multiplied f of x, let's say to the third power, f of x times f of x times f of x, we'd get this power rule. These other two limits, these special limits are a little bit interesting. They are intuitive. I'm going to draw the graphs for you so that you'll see that they are in fact intuitive. For the first one, we're going to draw, a function y equals c, meaning that it's just a constant. So here's a line, y equals c. And let's have a be here. And we want to know what happens as x approaches from the left and x approaches from the right. Well, no matter where we are, the output value is going to be c every single time because this is a constant function. So looking at the graph, that seems kind of obvious. For the second example, we're considering the function y equals x. Y equals x is when x and y have the exact same input-output values. So 1, 1 is on the graph, and 2, 2 is on the graph, etc. 3, 3, right? So let's take a value a here And we want to know what happens as we approach from the left-hand side and from the right-hand side. This output value here is also going to, let's, if this is negative a, this would be negative a, right? Or if I had positive a here, then this would be positive a here. All it's saying is because the x and the y values are the same, when I take the limit, the output value is going to be the same as the number that we're approaching. We can extend the power rule to take roots into account because they're related in terms of just being raised to an exponent. So we know that if we take the limit of something like x to the n power, x to the n power, and we're just taking a and plugging it in, we're going to get a to the n power. Similarly, if we're taking a square root or a cube root or etc., we'll be able to just plug those values in. What I have this down here, this root law, this is just kind of more generically putting these all together. But we'll go through some examples so that this will make a little bit more sense. These are just the sort of the formulas that we'll be using or the theorems we'll be using. All right, here's two examples. We want to evaluate the limit of each of these, and we're going to discuss, or we're going to write down what particular laws it is that we're using to evaluate. So for the first example, we have a polynomial, and we know that those sum and difference laws will allow us to split this up into separate components. So the first thing I'll do is I'll write the limit as x approaches 5 of 2x squared, and the limit as x approaches 5 of 3x, and the limit as x approaches 5 of 4. Again, we're using just the sum and difference rules. That allows us to split this up into separate limits. The constant multiple rule lets us take any constants that are multiplied in the front and that are multiplied and bring them out to the front. All right. We just did two examples that were related to this one and also this one. The last one is a constant function. 4 is a constant function. So no matter what value we're evaluating at, we're still going to get the constant as our output. So this part's going to be 4. For this one, we're looking at the line y equals x. And so similarly, whatever value we plug in, that's going to be the output value. When if I plug 5 in, I'm going to get 5 as the output value. These are the examples we were just looking up, we were looking at on the slide here, these special cases. So here, I'll have this negative 3 is hanging out on the outside, multiplied by 5. And then in the first part, if I put 5 into x squared, I know I'm going to get 5 times 25. Plug those all together into the calculator, and you should get 39. What's ending up happening, and I know some of you had calculus in high school, in particular cases, especially ones where we don't have any points of discontinuity or any areas where the domain is undefined, like in a fraction in a square root or something, we can really just take that value 5 and we could plug it into this function. If we just had plugged 5 in there, that would give us the 39, right? Let's see if that works here. What happens if we do that in the second example? What if we were to just take negative 2 and plug it in here? Let's see, negative 2 cubed plus 2 times negative 2 squared minus 1. 5 minus 3 times negative 2. I'll get, let's see, -8 plus 8 minus 11, or sorry, minus 1 over 5 minus 6, no, plus 6. So I think we're getting -1 over 11. Those 8s are going to cancel out. My point is that even though we've got all of these laws, we really don't have to go through all of the trouble to break everything into small components. If there aren't any issues, if we're not running into a place where something is undefined or we're doing something illegal algebraically, we can just take the number that we're trying to find the limit at and plug it into the function and get our overall value. That's what this slide is saying. It's called the direct substitution property. It's letting us know that we can, in fact, just plug the number in, provided that the function is continuous at that point, meaning that it's defined. It doesn't have an asymptote or a hole in the graph. Here's an example of one that we can't use the direct substitution because the function is not defined at 1. The denominator is going to be 0 if we plug 1 in. But what we'll do instead is we'll try to modify the function, like if we were to say factor it, into the top will factor into x plus 1, x minus 1. And so those are going to cancel. So instead, what we're doing is we're looking at the limit as x approaches 1 of the function x plus 1. We can plug the 1 in now and we can say that the answer is just going to be 2. This graph is going to look like this. It looks exactly like the line x plus 1. The only difference is that there's a hole in the graph right here when we're at 2. Or sorry, no, when we're at 1. Right? There's a hole in the graph. But we're still able to analyze because algebraically we were able to remove that discontinuity, and we can see from the graph that from the left-hand side and the right-hand side, they're both approaching the same output value. A couple theorems that we want to consider, and we had this in the last section as well, is that a limit exists if and only if the left hand and the right hand limits are equal to one another. So this would be the left hand limit, this is the right hand limit, and they have to approach the same number to say the limit overall exists. Number 2 is just sort of a stepping stone to give us theorem number 3. What it's saying is that if I have two functions, f and g, let's put f like this, and let's put g of x up here. It's saying that the function f is less than or equal to g, that when I'm looking at the limiting function, the limit of f is going to be less than the limit of g. It's just saying that the numbers are going to be lower because they're in a particular order. Seems kind of obvious. But the reason we're talking about that is because we need that for this squeeze theorem where we've got a function that's sandwiched in between two. We're going to consider the function g, which is sandwiched in between f and h. I've got a picture on the next slide to show you what's happening. Oh, here it is. This is the squeeze theorem. So g, you can see in this picture, is sandwiched in between h and f. And so when we talk about the limit, if h and f are sitting right on top of each other, we know that the limit of g has to be related to those two because it's in between both of them. In this example, we are looking at a piecewise function, and we want to know what the limit is as x approaches 1. From the left-hand side, we are approaching the output value of 2. From the right-hand side, we are approaching the output value of 2. And so we can say that the limit is equal to 2, even though the function is not defined there. I think we had an example like this in the last section as well. So even if the function is not defined at a particular point, if the left and the right-hand limits are equal, then we can say that that's the limit overall. All right, thank you for watching, and I will see you in class.